let's take a look at an example to get a better feel for this idea of diagonalizability. Okay, so we have a matrix A. It's a 3 by 3 matrix. And we're told some interesting information about matrix A. We are told A times vector 1, 1, 0 is the same as negative 4 times vector 1, 1, 0. Okay, what does that mean? Well, that means 1, 1, 0 is an eigenvector of matrix A, and negative 4 is an eigenvalue. Okay. So we have m1 equals negative 4, and x1 equals 1, 1, 0. And notice that's going to be the same for every statement here. The vector on the left-hand side and the right-hand side of the equation in each case is the same, which means that we are dealing with an eigenvector in each case, because A times the vector is just equal to a scalar times the vector. We're just scaling the vector, which means it's an eigenvector. Okay, so the second statement is saying that another eigenvalue of matrix A is equal to 2. Okay, and another eigenvector is equal to 2, 3, 0. And then statement 3, we have an eigenvector equal to 3 and an eigenvalue equal to 3 and a corresponding eigenvector equal to negative 1, 1, 1. Okay, well, great, but how does this help us? Well, remember what we just learned about diagonal matrices. Okay, A is going to be similar to a diagonal matrix D if D is equal to P inverse times A times P, where the entries of D are the eigenvalues of matrix A, and matrix P are the eigenvectors of matrix A, as long as we have n linearly independent eigenvectors. In this case, we're dealing with a 3 by 3 matrix, so we need 3 linearly independent eigenvectors. All right? It's not too hard to look at these and observe that they are going to be linearly independent. Okay, you can always check though if you need to. But these are 3 linearly independent eigenvectors, which means matrix A is diagonalizable. And we can use this relationship to find matrix A. Okay, so right now D is isolated in this equation. I'm going to just left multiply both sides of the equation by P, right multiply both sides of the equation by P inverse. That's going to give me P D P inverse equals A. So if I calculate P D P inverse, if I multiply them together, I can find A. So let's find D, let's find A. All right. So D is going to be my diagonal matrix where the entries are the eigenvalues. So my eigenvalues are negative 4, 2, 3. So negative 4, 2, 3. Okay, you could leave the zeros off if you want. I actually think it's a little easier to read if you do leave the zeros off. Very clear we have a diagonal matrix then, right? Notice that the order doesn't matter. So my eigenvalues are negative 4, 2, 3, but I don't have to have negative 4 here first. I don't have to have 2 here second. I could swap them if I wanted to. I could have 2 and negative 4 if I wanted, or I could swap the 3 and the negative 4, okay? As long as all the eigenvalues are there, it doesn't matter what order they're in. Okay, now let's find matrix P. Matrix P are the eigenvectors. Now again, it really doesn't matter the order they're in as long as it matches the order of matrix D. So in this case, The first eigenvalue in my diagonal matrix D is -4. So the first eigenvector in matrix P has to be the eigenvector corresponding to that eigenvalue of -4. Okay? That's 1, 1, 0. Since 2 is the next eigenvalue in matrix D, the next eigenvector in matrix P has to be the eigenvector associated with eigenvalue 2. It has to be the 2 eigenvector. Okay? That's 2, 3, 0. And finally, the eigenvalue for 3 is the last eigenvalue in matrix D. I'm going to take the eigenvector associated with eigenvalue 3. That's -1, 1, 0. That's going to be my last eigenvector, my last column of matrix P. Sorry, -1, 1, 1, right? Yes. Okay, so we have D, we have P. One more thing about matrix P. We have 3 eigenvectors here, okay? Remember that those eigenvectors, they really form the basis for an eigenspace, right? So there are going to always be infinitely many possible eigenvectors associated with each eigenvalue. So I have 1, 1, 0 here, but I could have also chosen maybe 3, 3, 0 because it's a linear combination of the eigenvector I have, right? It is a scalar multiple of the eigenvector I have. This would be fine as an eigenvector. You want to swap out 1, 1, 0 with 3, 3, 0? That works fine, okay? We can still get the right answer. So there are lots of ways to construct matrix D and matrix P. All right. The diagonal entries of matrix D have to be eigenvalues. The order doesn't matter as long as they're all there. Okay. The columns of matrix P have to be the eigenvectors of matrix A that correspond to the diagonal entries of matrix D, the eigenvalues in matrix D. Okay, but these can be any eigenvectors, so long as they're linearly independent. So scalar multiples are fair game, for example. Okay, all right. So with that out of the way, we have P, we have D. We need to find matrix A. Now, matrix A is going to be P times D times P inverse. So A is equal to P times D times P inverse. So let's plug in what we know. Matrix P, 1, 1, 0, 2, 3, 0, -1, 1, 1. Matrix D is the diagonal matrix with entries -4, 2, 3. And now I need P inverse. Okay. Now, P inverse, I will have to find the usual way. If I put P on one side of an augmented matrix and I on the other, and find the reduced row echelon form, I will get I on the left side of the augmented matrix, and then the columns on the right side of the augmented matrix will be my P inverse. That will be what I want here, okay? Do make sure you get the order right here. I want PDP inverse. P has to be the matrix on the left. Don't mix these two up, okay? It can be a little tricky because sometimes we write it this way and sometimes we write it this way. If we write it this way with the diagonal matrix, sorry, no, that's the same way. Sometimes we write it this way. That's what I wanted to show you. Sometimes we write it this way, sometimes we write it this way. If we write it this way with the diagonal matrix all by itself, then the P inverse goes first. If we write it this way with the non-diagonal matrix by itself, then the P inverse goes last. Okay? The matrix P is the one with the eigenvectors. So just, keep track of that. Okay, so we're going to need our calculator for this one. Let me pull it over. Okay, So we want matrix P, which we have right here, and we want to augment it with the identity matrix. So let me just write matrix P in first. So that's 1, 2, negative 1, 1, 3, 1, and then 0, 0, 1. And now I'm going to augment with the identity matrix. So the first row of the identity matrix is 1, 0, 0. The second row is 0, 1, 0. And the third row of the identity matrix is 0, 0, 1. Oops. And now let's find the reduced row echelon form. And there it is. Notice the right 3 columns is the identity matrix. It's the left 3 columns is the identity matrix. 1, 0, 0, 0, 1, 0, 0, 0, 1. It's the right 3 columns that we want, and that's going to be our inverse. Okay? So looking at that, my P inverse is 3, negative 2, 5, negative 1, 1, negative 2, 0, 0, 1. Okay, so P, D, P inverse. All right, we've done all the hard work. The only thing left is multiply the matrices together. We'll get matrix A. I'm not going to bore you with having you watch me multiply these matrices together. The answer that we get if we do multiply all the matrices together, matrix A is going to be negative 16, 12, negative 31, negative 18, 14, negative 29, 0, 0, 3. So that is how we can reconstruct matrix A, knowing only its eigenvalues and eigenvectors.